Pluto is a distant and baffling planet, which was once a member of our nearby planetary systems family. However, recent groundbreaking statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a startling revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we witnessing a fascinating cosmic phenomenon, or is there more to this looming colossal collision? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was downgraded to a dwarf planet mainly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading researchers, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both sounding the alarm about a potential catastrophic collision between these two celestial bodies, which could pose a significant threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution yet. The intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more extraordinary is its inclination. Tilted at 17 degrees to the ecliptic plane, Pluto's trajectory is much steeper compared to other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, contrary to what we might expect from their positions in the solar system. This raises the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to understand its peculiar trajectory. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit physically crosses Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of celestial mechanics. The three-body problem in space. Determining how three objects like Pluto, Neptune, and the Sun move and influence each other with their gravity is key to understanding this phenomenon. It's like trying to predict where these objects will go based on where they start and how they pull on each other. In Pluto's case, this problem highlights how its path, Neptune's path, and the Sun's gravity all interact in a complex manner. Terms like apsidal libration and resonance libration, along with the VZK oscillation, are essential parts of this puzzle. According to astrophysicists, what keeps all planets in their orbits is a phenomenon known as apsidal libration. For Pluto and Neptune, this means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is critical in preventing their orbits from meeting. Degree libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned well above their orbital plane, providing an additional layer of protection from potential collisions. Another key aspect of this situation is the VZK oscillation. Named after three scientists, von Zeipel, Kozai, and Lidov, who studied how objects move in space, this concept explains how the gravitational pull of three celestial bodies like Pluto, Neptune, and the Sun influences their motion. For Pluto, the VZK oscillation helps us understand why its orbit around the Sun is so unusual. Even though Pluto's path appears chaotic, this oscillation helps keep it moving smoothly for extended periods. The VZK oscillation demonstrates that even when space seems wild and unpredictable, certain patterns and rules maintain order. These factors help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or drift off course. This three-body problem helps us understand how these elements shift based on the gravitational interactions between these celestial bodies. Studying this teaches us more about Pluto, our solar system, and distant worlds and their stars. Numerical simulations in the late 1980s revealed that, despite these stabilizing properties, Pluto's orbit is intrinsically chaotic, with minor deviations in initial conditions leading to significant differences over millennia. However, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long time scales, effectively managing the chaos. Recent computational insights have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's path around the Sun. Neptune has a remarkable relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This relationship helps keep Pluto's path consistent. Yet Neptune isn't the only one helping. Jupiter's gravity also plays a significant role in stabilizing Pluto's orbit. In fact, Jupiter's gravity alone is powerful enough to ensure Pluto remains on a stable path for a long time, even billions of years. It seems Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely in space without running into trouble. These peculiarities are crucial in the broader context of the universe, maintaining the control and consistency of celestial bodies' movements. Without these elements, our solar system would be a far more chaotic and unpredictable place. Bodies like Pluto could potentially collide with others or be ejected from their stable orbits, impacting other celestial bodies. For Pluto, especially with discussions about it potentially colliding with Neptune in the future, understanding its orbit is vital. It provides a clearer picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of balance through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of constant observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the irregular nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's path on its initial conditions, is strikingly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can dramatically alter its long-term orbit. Using computer simulations has been incredibly helpful for scientists to figure out how Pluto moves in space. These simulations use advanced mathematics to model how Pluto and other space objects interact with each other. Neptune and Pluto pull on one another. By changing tiny details in the simulations, astronomers can see how even small changes can make a huge difference in where Pluto ends up. In the late 1980s, these simulations revealed something really interesting about Pluto's orbit. Even though it has things like angular momentum and resonance to keep it stable, its path can still be wild and erratic. If you start with just a tiny difference in where Pluto is or how fast it's moving, over many years, its path can end up looking very different. But even with this chaos, Pluto's orbit remains stable for a long time, like billions of years. This means Pluto's journey around the Sun has some sort of order to it, even though it might seem all over the place at first. Predicting infinite events, especially when they involve turbulent orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical simulations provide a powerful means to understand and predict the future behavior of celestial bodies, they also highlight the limitations of our predictive abilities. These models rely heavily on the accuracy of starting conditions and the complexity of the interactions they simulate. Any slight mistake or misrepresentation can lead to vastly different results, making precise predictions a daunting task. Moreover, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we've made great strides in understanding space, the case of Pluto serves as a reminder of how our knowledge of the universe is still limited. Understanding the gravitational effects of the giant planets on Pluto's orbit gives valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have significant impacts on the stability and trajectory of other bodies within the system. So, why are major astrophysicists only now raising concerns about a potential crash between Pluto and Neptune, despite all these complex forces working to prevent such an event? Neil deGrasse Tyson, a prominent astrophysicist and a key figure in popularizing cosmology, offers a unique perspective on the mysteries of our solar system, especially the fascinating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful discourse on the evolving nature of celestial mechanics and the public's fascination with the unknown realms of space. Tyson's position on Pluto's renaming is rooted in the ever-expanding knowledge of our solar system. He views the renaming not as a downgrade, but as an important adjustment to our growing understanding of the many bodies orbiting our Sun. His approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a sign of how much more there is to discover in space. The interest in these questions, particularly the possible interactions between Pluto and Neptune, highlights the dynamic and often unpredictable nature of our solar system. His work emphasizes that the more we uncover about space, the more questions arise, pushing us to explore further and refine our understanding of the universe. Michio Kaku, another renowned physicist and futurist, offers a complementary perspective on the mysteries of space, focusing on the often unpredictable forces that shape our universe. Kaku is known for his ability to connect complex scientific concepts with cutting-edge visions, making him a significant voice in discussions about celestial mechanics and their broader implications for humanity. Kaku's views on Pluto and its orbit underscore the need for continuous observation and advanced modeling to predict and understand potential cosmic events. He sees the interactions between celestial bodies as a critical area of study, not only for academic interest but for practical implications. The potential impact between Pluto and Neptune, for example, is not just a hypothetical scenario but a reminder of the dynamic and often chaotic nature of space. Kaku's futurist perspective urges us to consider the broader implications of such events, from the impact on our understanding of the solar system to the possible need for future space interventions. Kaku's viewpoint highlights the importance of being prepared for the unexpected in space. His work suggests that the more we understand the forces at play, the better equipped we will be to navigate and potentially mitigate the effects of cosmic events. Both Tyson and Kaku's perspectives converge on the idea that space is a realm of endless discovery, and that our current understanding, while vast, is still limited. Their emphasis on the need for continuous exploration and advanced modeling reflects the evolving nature of space science. They highlight the importance of not only understanding celestial mechanics as they are now but also speculating on how they might change in the future. The potential crash between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It underscores the need for rigorous scientific inquiry, cutting-edge technology, and a willingness to adapt our understanding as new information emerges. For Tyson and Kaku, the mysteries of space, exemplified by Pluto's orbit, are a call to action for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is a general scientific consensus that, for many years to come, the orbits of Pluto and Neptune will remain stable due to their mean motion resonance and the various gravitational influences acting on them. Therefore, a direct crash between Pluto and Neptune is highly unlikely. However, the complexities and potential perturbations in orbital elements mean astronomers must continue to monitor and study these celestial bodies to better understand their long-term behavior and any potential risks they might pose. While the possibility of a Pluto-Neptune impact remains largely theoretical and considered unlikely with our current understanding, it highlights the importance of ongoing exploration and observation in space science. Advances in technology, including improved telescopes and computer simulations, will help astronomers refine their models and predictions, ensuring we stay abreast of the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's renaming and Kaku's emphasis on the unpredictable nature of celestial mechanics both highlight the need for continuous investigation and an adaptable understanding of our universe. The potential crash scenario, while illustrating the dynamic and complex interactions within our solar system, ultimately reminds us of the vast, still unknown territories in our comprehension of space. Through ongoing research and observation, we strive to unravel these mysteries, ensuring that our knowledge keeps pace with the ever-advancing universe.